Okay. Thank you, sir.
Anyway, I will post the solution perhaps by Sunday or Monday. Let other people also do the problem. All right.
Sir, I had a doubt.
Yeah.
If can we keep the driving force or the temperature difference as one
Ah,
degree Celsius?
yeah. Good point. Uh, Now, okay, let us spend some time in talking about that.
So because then
Yeah,
the latest.
I agree with you. I agree with you. I will tell you the implications,
Okay, sir.
and then you decide whether it is good to keep 1 degree or more than 1 degree. So, whatever this was, suppose coming in at 100 kg per hour, right? What did we take? 100 kg per hour.
So your screen isn't visible.
Oh, I have not shared your screen.
Sir,
Sir,
it
it
is
is
visible.
visible.
Sir, it
Okay,
is
sir,
visible, sir.
Ah, okay,
I'll
okay.
reload it.
Ah, uh, when I was explaining to your query, was the screen visible to you?
Yes, sir.
Ah, okay, okay. Otherwise, I was drawing control volumes, and uh, if it was not visible to you, it will be difficult. Are you able to see?
Sir, I'll try again. You can continue. I'll rejoin in a second.
Ah, you rejoin. We will wait. Otherwise, how will your query get answered if you don't see?
Sir, sir, in multiple step evaporator system, we
Uh,
can take any number of
Yes,
evaporators.
sir, it's visible, sir.
yeah, thank you. Yes, Praveen, we can take any number. I think the problem that is solved, it takes 3 evaporators or 4 evaporators. But yes, you can take any number. People have gone to as large as 30, 40 also. To that extent, the steam economy will be better and better.
Sir, can you
Okay, sir.
explain steam economy?
Yeah, there is a solution. I will put it in the solution video. It is there already in the solution video. You can check the solution video. I will not post it today. Maybe another. Unless if everybody has attempted the multiple effective evaporator problem, I can post the solution today also. But if people want to attempt, I will post the solution later. Yeah, Arya.
Yes,
Um,
sir.
here is what. Here are some thoughts. Okay, now you decide whether you want driving force as 1 or 20 or 30 or 50 or 100. Okay, I don't want you to take a decision now, because that will depend even more when you start doing heat transfer course in semester 5. But I just want you to be aware. Now, if you think about what is happening, this many kg per hour of 3% NaCl at 30 degrees centigrade is coming in. Water has to be evaporated. How much, I don't remember how much it was. I think it was 94 kgs.
94, sir.
Yeah,
94
94
kg,
kg
sir.
per hour. And then we had 6 kg per hour of this salt solution. So that means we need to supply heat to the solution at a certain rate, so many kilocalories per hour, right? Do you agree with that? That heat
Yes,
has
sir.
to be transferred from outside of this evaporator, from the jacket to inside. Do you agree with that?
Yes.
Now, if the outside is at 137 degrees centigrade, You remember when we were doing the wet bulb temperature problem? This is your rate of heat to be transferred. What was it dependent on?
Temperature difference.
Correct. It was dependent on the temperature difference. It was also proportional to the area of heat being area through which heat is being transferred. In this case, the area through which heat is being transferred is this vessel area. So the circumference of this vessel, pi into d, multiplied by the height, that will give you the surface area. So this is, suppose this height, this is your height h, this is your diameter d. Assume it's a cylindrical vessel. So if it is a cylindrical vessel, surface area through which,
H into pi d.
yeah, through which heat is being transferred is going to be pi into d, the perimeter circumference, into the height, the curved surface area of the cylinder, right? So this is nothing but pi into d into h. And the proportionality constant, what did we call that proportionality constant?
Heat transfer coefficient.
Correct. Heat transfer coefficient. We denote it by a symbol h. Now this heat transfer coefficient, as we will see in semester 3, semester 5, this heat transfer coefficient depends on how fast I am agitating. It does not depend on the temperature difference. So if I have to transfer a certain rate of heat, if I reduce this temperature difference, instead of 137 and 117, if I make it 118 and 117, this area will have to be
Increased.
20 times increased. Instead of 20 degree difference, if I make delta T as 1 degree, then I will have to make it 20 times more area. 20 times more area means I will have to buy a bigger evaporator. Either diameter has to be bigger, or height has to be bigger, or both have to be bigger. So I will have to buy a bigger vessel. What is that going to do?
Cost of the apparatus would increase.
Correct. Cost of evaporator will increase. It may not increase by 20 times. It may not increase by 20 times, but certainly it will be higher. By how much it will increase, we can estimate that. That's one of the jobs of chemical engineers. How do you estimate costs? So if I plot delta T, driving force between the inside, outside and the inside, say 1 degree or 20 degrees centigrade, my cost of evaporator is going to come down if I plot a graph of cost of evaporator. Correct? Do you agree with that?
Yes, I agree.
This may not be 20 times. This difference may not be 20 times. Let's not worry about how much this difference is. But it will be certainly much more if the evaporator size is bigger. All right. So then next thing that you will ask is, then why not increase it to 30, 40, 50, 60, 70, 80, 90, 100? And this will keep
But
on.
then the material should be that much conducting or other things.
Correct. Other things will, what is the other thing that is going to change? If this is at 137, suppose it is at 137, what was the pressure of the steam?
3.3 bar.
3.3 bar. Now suppose I make the driving force 40 degrees, instead of 137, I make it 157. What will happen to this pressure?
This will also increase. So the pressure bearing capacity should also increase proportionally.
Correct. And then for the, even if the size of the evaporator goes down, my cost of the evaporator will go up, because I would need to make it withstand higher and higher pressure. If I want it to withstand 3 bar pressure, I will have to design something. Now, how to design something for 3 bar pressure versus, let's say, 10 bar pressure, that is something that is going to come in your semester 4 and semester 6 and semester 8 process equipment. There is a course called as process equipment design, where you will design the equipment for different pressures, maybe 3 bar, 5 bar, 10 bar, 20 bar, and see what happens to the cost of that equipment, or what happens to the other things that are required in that. So this is not going to be a monotonous decrease. Beyond a certain point, it may actually go up.
Increase.
Okay. So those are some of the things that you have to worry about right now. All these things we will do as we go along in our 4 years. So right now I just wanted to give you some number. So I gave you some number of 20 degrees centigrade. All right.
Yes, sir. Understood.
Any other doubt?
No, sir.
Okay. Can we
Excuse me, sir.
Yeah.
Now we are considering the ideal situation. That's why we are not considering the heat loss in form of the vessel. Like some heat will go in heating the vessel as well, right?
Yes, but Ansh, it is at steady state, right? So
Yes, sir.
this vessel also is at a steady temperature. This vessel itself is also at steady temperature. But yes, you're right. We are not worried about heat loss to the surroundings. Your surroundings are going to be, let's say, 30 degrees centigrade. This vessel, this solution is going to be hot. It is at 117 degrees centigrade. This outside surface of the jacket is going to be at 137 degrees centigrade. So there is going to be some loss from the evaporator to surroundings, because this is at high temperature, let's say 137 degrees centigrade, surroundings are at 30 degrees centigrade. So there will be loss of heat by way of conduction, by way of convection, by way of radiation, right? So yes, you are absolutely right. We need to estimate heat loss. So when we write our enthalpy balance, now we write our enthalpy balance on this control volume. Let's give some stream numbers. Let's call this as stream number 1, stream number 2, stream number 3, stream number 4, stream number 5. Now when we write heat balance on this yellow control volume, we will have to write heat coming in must be equal to heat going out. Heat coming in is because of stream 1 and stream 2 into this yellow control volume, 1 and 2. Heat going out is from 3 and 4 and 5 and loss to surroundings. So when we consider loss to surroundings, the amount of steam required is going to be even more. We had got as 37 kgs of steam per kg of salt without considering heat loss. If you consider heat loss, this 37 may become 40. Okay, Ansh?
Yes, sir. Yes, sir.
Absolutely right. So how to estimate heat loss? That's going to be a part of heat transfer course. Semester 5. Okay. So what you do to reduce this heat loss is to put insulation, glass wool, kind of
Basically an
insulation. So many
adiabatic
other,
wall.
yeah, try to make it as adiabatic as possible so that there is no heat loss or heat gain from the surrounding. So this is a situation of heat loss from the surrounding, but because temperature is larger than the outside temperature. But suppose I could be doing some cryogenic process, like I could be doing distillation of nitrogen and oxygen. So maybe this temperature would be, let's say, minus 77, no, not minus 77 Kelvin. So outside is hotter now, then heat will come in to this control volume from outside by convection radiation. So we will have to write heat coming in plus heat coming in from surroundings, right? So depending on that, we will have to write differently our heat balance, heat in, heat out. All right.
Yes, sir.
So what kinds of insulation are there, how to calculate that, how to decide on how much insulation I need, all those things will come in your heat transfer course. Okay, shall we go forward? It is good thing that we are having discussion. Shall we go forward?
Yes, sir.
Yes, sir.
Okay,
Yes,
so
sir.
I had asked you to revise about your 11th and 12th standard concepts on thermochemistry. So just to refresh your minds, we write under standard conditions, which means 25 degrees centigrade, 1 atmosphere absolute pressure, standard heats of formation. So standard heat of formation of SO2, meaning synthesis of SO2 from its elements in their natural state, in their standard state. So under standard state, sulfur would be in the solid condition, solid form, oxygen would be in the gas form, and I will get SO2 would be in the gas form. Sulfur in the solid form combining with 3/2 oxygen in the gas form, giving me SO3 in the gas form, because at 25 degrees centigrade, 1 atmospheric absolute pressure, 1 atmosphere absolute pressure, that is a standard condition. Our sulfur is in the solid state. Oxygen.
So it depends on which solid state also, right?
Yeah, correct. Right now, let's not worry about that just now. Different allotropes of sulfur we will not worry about just now. Yes, some energy would be required to convert one to the other as well, but we are saying that whatever is the natural most thermodynamically stable form, it is that form. Okay, so this is called as standard heat of formation. We are denoting that standard condition by a subscript 0. Subscript 0. 0 doesn't mean it is 0 degrees centigrade. 0 means it is a standard condition. So these are called as standard heats of formation. Okay. Now, if you want to find out the heat of this reaction, what I will need to do is I will need to take reaction 2, subtract reaction 1 from that, then I will get this reaction. Do you agree with that? So the standard heat of reaction, this reaction is going to be the standard heat of reaction 2 minus standard heat of reaction 1. And standard heat of reaction 2 is nothing but standard heat of formation of SO3, and standard heat of reaction 1 is nothing but standard heat of formation of SO2, right? So it would be minus 395 minus 296, right? What was the value?
Minus 98.28.
98.28 units.
Kilojoule per gram mole.
Right, it is kilojoule because the standard heats of reaction I have told you in kilojoules. Fortunately, both of them are in the same units. If they are in different units, you will need to convert them into the same unit, and then you can do the subtraction. And we are writing this reaction for per gram mole of SO2. We are writing the reaction like this, right? So this is kilojoule per gram mole of SO2, or standard heat of reaction per gram mole of SO3. It is one and the same, but it is minus 98.28 kilojoules per 0.5 gram mole of oxygen. Do you agree with that? Stoichiometry. So if I want to write this heat of reaction, delta H under standard condition for this reaction would be minus 98.28 kilojoule per 0.5 gram moles of oxygen. If I want to write it per mole of oxygen, it would be minus 98.28 into 2 kilojoules per gram mole of oxygen, right? Pay attention to the stoichiometry. 1 gram mole of SO2 reacts with half a gram mole of oxygen to give us 1 gram mole of SO3. Are you comfortable now? So heat of reaction we could be writing per mole of oxygen. We could be writing it as per mole of SO2, or we could write it in terms of per mole of SO3. To that extent, the magnitude would change. Do you agree with that?
Yes, sir.
So what we are saying is the standard heat of reaction is equal to summation of standard heats of formation of products. I could have multiple products here, and summation of standard heats of formation of all the reactants. All the reactants, SO2 is one reactant here, oxygen is one reactant here, but oxygen is in its natural state. Therefore, the standard heat of formation of oxygen is 0, right? So therefore, this is just equal to delta H0 SO3 minus formation of SO3 minus delta H0 formation of SO2 plus 0.5 into standard heat of formation of oxygen. But this is just 0. By definition, standard oxygen in its standard state heats of formation is taken as 0. Do you remember from that your do you remember this from your thermochemistry?
Yes.
Yes, sir.
Yes.
Yes, sir.
Yeah. Okay. Okay. So sometimes we might be given heat of combustion. So for example, let me give you a reaction. Let me just come to that. One second. Let me just open that page. Combustion we have. Okay, suppose we take some reaction. Let's say methane gas plus plus CO2 gas, giving you CO gas and hydrogen gas. Steam reforming, dry reforming of methane. Okay, or maybe we will take a slightly different reaction. Carbon monoxide plus hydrogen giving us methanol. Right. We have seen this reaction. Let's take this reaction. Okay. Do you remember this reaction? I think I will take this first reaction only, because in methanol we will talk about little later. CH4 gas plus CO2 gas giving you CO gas plus hydrogen gas. Right? Do you agree with that? This reaction have you seen? Do you remember?
Yes, sir.
Yes, sir.
Yes, sir.
Can we balance the reaction? Tell me the balanced reaction.
Two CO plus
Yes,
two
sir.
H2.
CH4 plus CO2 gives 2CO plus 2H2.
Right. Now, if I want the standard heat of reaction, standard, remember standard means 25 degrees centigrade, 1 atmosphere absolute pressure. What I may be given is I may be given heats of combustion. Okay, I will give you the heats of combustion. I will show you also heats of combustion. I will share that on the screen. So let's say heats of combustion of methane. So when we say heat of combustion of methane, what we are meaning is we are saying that methane will combust with oxygen and give you CO2 gas and H2O. Now what should be the state of this H2O?
Liquid.
Liquid. Why is that?
More stable.
Not more stable. It is not a question of more stable,
It's
less
zero,
stable.
sir. At 25 degrees
It is
Celsius.
in what state it exists at 25 degrees centigrade, standard conditions. Right? Why water exists in the liquid state at 25 degrees centigrade 1 atmosphere is because it is more stable. So your answer was not wrong, but water in the liquid state at these conditions is more stable than water in the vapor state or water in the ice state. So we will see in semester 3 how to calculate stability of these things and how to calculate the Gibbs free energy, which is going to decide the stability. But okay, right now let's not worry about that. Under the standard conditions, water exists in the liquid state. Okay. Now CO2, obviously there is nothing more. It cannot combust to anything more. CO plus oxygen gas giving you CO2 gas. That's the heat of combustion, right? And we'll have to balance it. We will have to say half of oxygen. And hydrogen gas plus half oxygen will give me H2O liquid. Now, where do we get these standard heats of combustion from? Okay, so you can ask Google, or if you have your Himmelblaus book, let me open the book and let me show you. One second. Okay, so let me share this. Okay, so if you look at the Himmelblaus book, if you have, you better have. There are appendices at the end, and one of the appendices, appendix D in this particular case, is heats of formation and heat of combustion. Are you able to see?
Yes,
Yes,
sir.
sir.
Appendix D is your heat of formation and combustion. So if you click on that, it gives you the heats of formation and combustion. Let's see what it, let's read what it says. Okay, it says heats of combustion formation and heats of combustion at 25 degrees centigrade. That's the standard state. And standard state of products are CO2 gas, H2O liquid. See that? Nitrogen gas, SO2 gas, HCl in the aqueous state. Okay. Now let's take all our components. First component is methane. So if you go down, so these are the standard heats of formation. This is the standard heat of formation in terms of kilojoule per gram mole. And this is the standard heat of combustion in terms of kilojoule per gram mole. You are able to see, right?
Yes, sir.
Yes.
Yeah. Let's look
Yes,
at
sir.
methane.
Yes, sir.
Yeah. Let's look at methane. Let's go down. Let's see methane. Here is methane. Methane, molecular weight is there, gas state. Standard heat of formation is minus 74.84. Standard heat of combustion is minus 890.4. Are you able to see?
Yes.
Yes, sir.
Okay. Carbon dioxide, that's our next reactant. Obviously, that is the most oxidized state. There's no way carbon dioxide is going to get combusted into something more. Next is carbon monoxide, right hand side. Carbon monoxide. So here is our carbon monoxide. Gas state, standard heat of formation is minus 110.52. Standard heat of combustion is minus 282. Minus 282.99. Right? Do you agree?
Yes, sir.
Hydrogen, H. That's our last product, hydrogen. You see this? Standard heat of formation is 0. Right? Element in their natural state, 25 degrees centigrade, 1 atmosphere. Heats of formation are taken as 0. Heat of combustion of hydrogen, minus 285.84. Are you able to see?
Yes, sir.
Right? So let's write them. Okay. I will stop sharing. Let's write them here. Let me share now again our notebook. Okay. So standard heat of combustion, let me write them here. Okay. Delta H0C. For methane, what was the value? Minus 890.4. For carbon monoxide, standard heat of combustion, what was the value? Minus 282.99. Next, hydrogen, minus 285.84. Minus 285.84. Now, using these standard heats of combustion, can you tell me the heat of this reaction under the standard conditions?
Yes, sir.
So calculate.
Sir, I am getting 247.26 kilojoules per mole.
247.
0.26
I forget that 0.26 units.
kilojoule per mole of methane.
247 kilojoule per gram mole of methane.
Yes, sir. Same. 247 point.
Yes, sir. 247.
Is it positive or negative?
Positive.
Positive, sir.
Okay.
Positive 247.
Yeah, meaning what? Is it exothermic or endothermic?
Endothermic.
Yeah,
Endothermic.
means I will have to supply heat to maintain the same temperature, to maintain isothermal conditions, and if I don't supply heat, the products will cool down. Anybody else gets any other answer?
So got the same answer.
So same answer.
So many people actually did, or I'm just writing? 50 people got 247. I don't think there are 50 people in the class at all. Oh, there are just 50 people. Lucky. Any other answer? Anybody stuck? Anybody?
1 minute, sir.
Okay, okay. Take your time.
Excuse me.
Yeah. Yeah, go ahead. Wanted to ask something?
Yes, sir. So I'm getting the answer minus 247, sir.
Maybe you are right. Other 49 are wrong.
So even I got plus 247. Uh,
Okay. So Hardik, you are the only one who's right. Maybe all other 49 are wrong. Maybe. Should we discuss?
Sir, I also got positive for 247.
Thank you, Alankar.
Yes, sir.
Thank you, Alankar. Thank you, Om. Should we discuss? Hardik? Hardik gave minus 247, right?
so I got my mistake, sir. It's plus 247.
Ah.
Yes, sir. Plus 247.
Yes, sir.
Okay. All right. So just to tell you, how do I get this? If you want to get this reaction from these reactions, what will I need to do? I will have to eliminate oxygen. I will have to eliminate water from the set of these reactions, right? So if I multiply this by 2, if I multiply this by 2, is it? What do I need to do? Do I need to multiply by 2? Do I need to multiply by 3? Well, the first reaction itself is not balanced properly.
Yes, sir.
Right? So I will have to say 2 and 2. Now it is balanced. So if I say this is our reaction 1, reaction 2, reaction 3, if I do reaction 1 minus reaction 2 minus reaction 3, this will give me our reforming reaction. Let's call this as reaction 4. Right? So heat of reaction 4 would be heat of reaction 1, first reaction, minus 2 times heat of reaction number 2, minus 2 times heat of reaction number 3. So heat of reaction for reaction number 1 is nothing but standard heat of combustion of methane minus 2 times standard heat of combustion of carbon monoxide minus 2 times standard heat of combustion of hydrogen. Right? So that will give us our heat of reaction for our reaction number 4. That is what we wanted. So it is nothing but summation of all the standard heats of combustion of reactants minus summation of all the standard heats of combustion of products. Do you agree with that?
Yes, sir.
Okay. So let's actually get the value. So it is minus 890.4 minus 2 times minus 2, this also will have to multiply by 2, minus 282.99 minus 2 times minus 285.84. Right? So this will be plus 247 kilojoule per gram mole of methane. How we have written the reaction? We have written it per gram mole of methane. So this will be the same as 247 kilojoule per gram mole, kilojoule per gram mole of carbon dioxide. Stoichiometry 1, 1. But the stoichiometry is 2 and 2. Right? So this would be, it is same as 247 kilojoules per 2 moles of carbon monoxide, or it would be 247 kilojoules per 2 moles of hydrogen. If I divide this by 2, it would be 123.5 kilojoule per gram mole of carbon monoxide, or 123.5 kilojoule per gram mole of hydrogen, which means as if we are writing the reaction as half plus half, giving us 1 plus 1. Right? Is that clear? Is that okay? Yes, no, can we go forward?
Yes,
Yes,
sir.
sir.
Okay.
So,
Yeah,
one doubt.
yeah, Arya.
So, what does combustion at 25 degrees Celsius mean? Does it mean the reaction only, or like literal sense of combustion that we are speaking of?
Yeah, literal sense of combustion, because I can burn something and keep temperature at 25 degrees centigrade. So so where do you think these values come from?
So,
We got it.
as in,
No, just let me answer. Where do you think these values come from? It came from book. Where did these values come from in the book? And suppose you have made a new product which has some weird structure. I can't even draw weird structures, but let's say you make a product and you don't want to tell anything about that product because it is so secret. You are going to make trillions of dollars from this product. But for, let's say, for designing something, you need heat of combustion of that product. Now, how do you get that data? Because it is a secret product. You are not going to tell anybody. It is nobody else in the world has found this product. You are the one who has found this product. So no data is available on this product. No book, no Google, no Wikipedia, no any other source, LinkedIn, Facebook, Twitter, Instagram. Nobody has any data on this product because nobody knows this product, right? So what you do is you need to measure the heat of combustion. One of the ways in which you measure heats of combustion is called as calorimeter or a bomb calorimeter. There is one problem in the sheet that I will share with you related to this bomb calorimeter. So what you do is you take a rigid vessel, you put your substance in it, you put oxygen in it, you put this whole thing in water, you nicely insulate it, put tons and tons of insulation, okay, and you provide a spark or you provide a source of ignition. So your secret product will burn, heat will be released, and the temperature of this bomb calorimeter, this vessel and the water will increase. And you measure the rise in temperature. From that you can calculate how much heat it must have liberated by way of combustion. That's how you measure heats of reaction, right? So then you are measuring at 25 because your substance is so small a quantity. Your oxygen is there. You have large amounts of water. So you don't allow too large a change of temperature. Maybe 25, it goes up to 30, 35. So you will get standard heat of combustion, right? So it has to be measured. Do you agree with that, Aryan?
Yes, sir. But, like I was thinking that would it be just oxidation at 25 degrees? Like it wouldn't. Okay, I understood.
It would not oxidize. It would not oxidize if you keep it as such. But if I provide a source of ignition, it will combust because at that local hotspot, local temperature, it has increased and therefore it can combust. So when I say something combusts, what actually do we mean? Let's say we have a piece of wood and we have oxygen, right? Or coal if you want, or air. Now this is stable, right? It is not going to combust.
Yes, sir.
Unless we provide a source of ignition. What is the source of ignition? I will take a matchstick and I will bring that matchstick here. So the local temperature becomes high. The wood starts pyrolyzing. The pyrolysis gases come out at high temperature and then they combust and we get a flame here, right? And then it is possible to burn this wood. But now if I put this inside a bomb calorimeter, then I can measure the heat of combustion of this wood at 25 degrees centigrade. Well, I'm allowing it to burn at high temperature, but overall what I'm measuring is the change of temperature of lots and lots of water. So it allows...
Yes, sir. Actually, my doubt was over there only, that we are allowing it to burn at a higher temperature. So how can we say that it's at 25 degrees?
Because overall the amount of heat released, because finally everything is coming back to 35 degrees centigrade or 30 degrees centigrade. Overall we are allowing it to rise only by 5 degrees centigrade. Enthalpy is a state function.
Understood, sir.
All right. So wood plus oxygen goes to high temperature, CO2, H2O. We cool, I get CO2, oxygen at 30 degrees centigrade. This is our overall reaction, state function. Right?
Yes, sir.
All
Understood.
right. Okay. Okay. Another thing that you would have learnt in thermochemistry in 12th standard is how to estimate heat of reaction at different temperatures. Did you learn that in your 12th standard? Yes, no? So CH4 gas plus CO2 gas giving us twice CO gas plus twice H2 gas. Standard heat of reaction is 247 kilojoules per gram mole of CH4. Suppose I want to conduct this reaction at, let's say, 1000 degrees centigrade. It's a reforming reaction. Reforming reaction happens at high temperatures, 1000 degrees centigrade. What is the heat of reaction at 1000 degrees centigrade? Can you tell me? Can you calculate? How do you calculate? You must have done in your 12th standard. Yes or no? No? Yes, no? Somebody say something.
Sir, faintly remember it. I don't know
Faintly
it
remember.
now.
Sir, is
All
this the only information,
Only?
or is there more information, or is this the only information?
No. Did you do this in your 12th standard, or you didn't do in 12th standard?
I don't think so, sir.
Yeah, how is it possible? I'm not saying I have given you all the information. You may ask me more information if you want. You should be able to tell me how to calculate. You may not tell me actual value, but you should be able to tell me how to calculate based on all the things that we have done.
Sir, do we have to use delta H equals to delta E plus RT delta N?
I have no idea what
Some
you have to
kind of that.
use. You tell me how to do it. You tell me how to do it. I will write it down. I will not say whether it is right or wrong just now, because I want other people also to write something.
So can we use delta G?
You tell me what to write, how to solve, how to find. I will write that.
So with heat capacity, we can find out.
You tell me how to do it. Not just with heat capacity, without heat capacity. I don't know. You tell me.
Sir, I am able to recall a formula.
You are able to recall a formula. Okay.
We need to calculate delta RCP for this reaction.
I have no idea what Mayur you are talking about.
Sir, the change in specific heat for the
That's
reaction.
what Ruchita was saying, something like that. Ruchita, is that what you are also trying to say?
Yes, sir.
I don't know. I don't know what you people have mugged up.
Sir, but for that we need individual delta RCPs.
तुमको जो चाहिए data, I will give you. You tell me what data you require.
Sir, CP for CO, H2 and all the reactants.
So take out Himmelblau's book. Look at one of the appendixes. one of the appendices tells you the heat of Cp values.
Okay,
Have
sir.
you heard of this law? Some law that you must have mucked up that starts with the word K.
Kirchhoff law, sir.
Kirchhoff.
Kirchhoff law, sir.
Atharva, you're right. Do you remember that? You have seen in your 12th standard?
Yes, sir.
Now you recall?
Sir, delta H final is equal to
Delta H final. What is final?
means at that temperature you want to calculate.
Means at 1000 degrees centigrade. Oops,
Is equal
not
to
100, 1000 degrees centigrade.
delta initial temperature. Delta at initial temperature.
Initial name, what is it? There's nothing like initial.
25 degrees, sir.
Standard heat of reaction, that is
Yes,
at
sir.
25.
Plus integration of 25 to 100,000 Cp delta T.
Cp what? Cp of which component? Hydrogen, carbon monoxide, carbon dioxide, methane, which one? Every one will have different Cp, right?
CP of reaction, sir.
Reaction, sir.
Cp of what?
Reaction.
Cp of reaction.
Even-
What is Cp of reaction? So far I have heard of Cp of a compound.
So you want to calculate of mixture, sir.
Mixture, which mixture?
Means CH4 and CO.
That mixture.
Yes, sir.
But the products are also there, no? Carbon monoxide and hydrogen.
So the stoichiometric coefficient of the products into the Cp of products minus the stoichiometric coefficient of each individual coefficients into individual Cp's of the reactants.
ये तुमने मकअप किया? Atharva, you have mucked up.
Yes, sir.
Huh?
Yes, sir. Means I learned just formula, sir. I don't.
You understood?
Now I get it, sir.
Can you derive?
No, sir.
Why not?
I want to check it again, sir.
How many people can derive this formula? I have given you enough information to derive this formula. Even if you don't remember anything from 12th standard, you can derive this formula even based on what we have discussed in last 4 lectures, or maybe 3 lectures. I will give you a chocolate to all those who can derive this formula. You have to tell me how to derive. I'm not saying it is right or wrong. Huh? It may be wrong also. Take 5 minutes, tell me how to derive. Even if you don't remember anything from 12th standard, even if you have not passed 12th standard, just based on the lectures, you should be able to derive. One chocolate of any size, any brand, any weight. Size and weight are different things. Nobody likes chocolates, looks like. You people don't like chocolates.
So basically, we are raising all the reactants and products to the elevated temperatures, and the heat involved in that is considered by the integration factor.
You tell me how to derive.
Sir, by graph.
Graph, which graph?
Sir, the delta H of that reaction versus their
You want to share your
temperature.
screen?
Temperature graph.
You want to share your screen?
Sir,
Yeah, Rishabh.
sir, heat capacity at constant pressure is equal to change in enthalpy upon change in temperature.
So,
So, sir, the temperature goes with C, and you can integrate it.
now, how do you get this formula?
We have
How do you
learned
get
this
this
in
formula from here?
well, change in enthalpy is written as enthalpy final minus enthalpy initial.
Are we having final and initial, or are we having heat of reaction? Are they
Yes, sir.
same?
Heat of reaction at a
Delta H and
temperature
H are
T2.
same?
No, sir.
And then?
The heat of reaction at temperature T2 and heat of reaction at temperature T1.
So how do you say that H final minus H initial is same as delta H minus delta H? I will have to say delta. Is that what you are saying? Rishabh, you are saying dH is equal to Cp dt.
Yes, sir.
So I should just draw triangles on both sides. Is that what you are saying?
No, sir.
Is that what you are saying?
No, sir.
Then what are you saying? Multiply by delta on both sides. Is it multiplication?
No, sir.
Then what are you saying? Praveen, you want to share your screen and you want to tell us what are you talking about? I'm not at all clear what you're talking about.
Excuse me, sir.
Yeah, Rishabh.
Sir,
Yeah, Nishant.
sir, we can find enthalpy change for all individual components, and at last we will add them.
Nishan, you want to share your screen and show us how to do? How
No,
to derive?
sir. Okay, sir. I'll tell you.
Oh, why tell me? Why not share your screen and show me?
Sir, I have not done on screen. I have written a notebook.
On notebook, okay.
Sir, I'll tell just two
Point the
equations are
notebook
there.
write it on the notebook and point it to the camera and share the camera feed.
Wait, sir. 2 minutes. I'll try.
Okay. Praveen, you want to share your screen? You want to share your notebook? Photograph of your notebook?
Sir, I have not done anything to represent.
So we are talking in air. हवा में बात कर रहे हैं सब लोग. Isn't it? If you have not written anything, on what basis are you making statements? Use graph, this, that. What graph? If you want to think about enthalpy versus temperature.
Sir.
Yeah, Rishabh.
Yes, sir. So we can write the Cp is equal to del H by del T, and we can write enthalpy change as enthalpy of product minus enthalpy of reactant at temperature T1.
Hey, wait, Re Baba. Delta H is not this. It is not heat of reaction. Cp is not related to heat of reaction. Cp is not heat of reaction. Change of heat of reaction with temperature. That's not Cp. Only problem is English language is only 26 alphabets. So we use H for enthalpy, we use H for humidity, we use H for heat of reaction also. Delta H for heat of reaction also. Can we use H for
Excuse me, sir.
magnetic field strength also?
Sir,
Yeah.
So we can take a reference as like at 0 degree Celsius, all CH4, oxygen,
You want
CH4 and
to
carbon.
you want to write in your notebook and share a photograph,
So I'll try, sir.
because without that we can't understand anything.
So it is a enthalpy versus time graph only, sir.
Enthalpy versus time. Now time kahan se aaya abhi?
Temperature. Sorry, sir.
That's the
Temperature.
problem. English language is only 26 alphabets. So T sometimes stands for temperature, T sometimes stands for time also. We need a language which has about 500 alphabets. Then there'll be no confusion. Okay, stop whatever you are thinking. If you want to think about this enthalpy versus temperature, suppose I take my reactants CH4 and CO2 at 1000 degrees centigrade and I convert them into my products, 2 carbon monoxide plus 2 hydrogen. In going from this reactants to this products, whatever is the enthalpy change that is taking place, this is nothing but our heat of reaction at 1000 degrees centigrade. Do you agree with that? These are our reactants. These are our products. If you think about a graph of enthalpy versus reaction coordinate, or reaction, I should not, coordinate word is frightening, progress of reaction. So 0, 100, our reactants are here, products are here. So reactants go to product like this. This is our energy of activation. And this difference is your heat of reaction. Do you recall? Yes or no? It could be exothermic, or like this, or it could be endothermic, like this. Reactants, they go to products. This is your energy of activation, and this is your heat of reaction. Do you agree? Do you disagree? You had seen this kind of graph anytime?
Yes, sir.
Yes, sir.
So if I translate this graph, this is at a particular temperature. If I want to take reactants, methane and carbon dioxide, to products, 2 of carbon monoxide and 2 of hydrogen, going from this point, let's say point 1 to point 2, that's our heat of reaction at 1000 degrees centigrade. Do you agree with that? Whatever is the enthalpy change, that's our heat of reaction at 1000 degrees centigrade. Do you agree with that? Yes, no? Yes or no?
Okay.
Only Sarthak is agreeing. Other 48 are silent.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
3, 4, 5. 5 people. Rest 40.
Sir, could you please repeat?
What I'm saying is, when we talked about enthalpy versus temperature, we said H2O liquid to H2O vapor. What did we call this as?
Enthalpy of latent heat.
Latent heat, lambda, right? Can we not say it is like this? heat required is latent heat. Yes or no?
Yes, sir.
Right. Suppose I say this is my reactant and this is my product. Can we not say that lambda is like heat of reaction of this reaction?
Yes, sir.
Yes, sir.
Right. So if I want to take methane and carbon dioxide at 1000 degrees centigrade. Oh, I have written 100. Sorry, I should write 1000. 1 second. Where did that go? Yes, I have written 100. I should not write 100. I should write 1000. I want to take reactants at 1000 degrees centigrade to products at 1000 degrees centigrade. What are the products? 2 carbon monoxide and 2 hydrogen. You are able to see the screen, right?
Yes, sir.
Yes, sir.
Yes, sir.
Right. So if you want to write on this graph enthalpy versus progress of reaction, 0 progress, 100 progress. 0 progress means what? Reactants. 100 progress means what? Products. Right? How does the reaction happen? Like this, right? Energy of activation and heat of reaction. Isn't it? Yes or no?
Yes, sir.
Yes,
Yes, sir.
Suppose I am drawing this graph at 1000 degrees centigrade. Can I look at the plan view of this graph? Or not plan view, I should not say plan view. I should simply say side view. Can I look at it from this side? What will I see? Engineering graphics. You had a course on engineering graphics?
Yes, sir.
Yes, sir.
If I see from side view, what will I see?
Straight line.
Straight line. Reactant is here. Highest energy of activation state is here. Products are here. How it is going? Reactant, it is going to that highest state of energy of activation, highest activated state. It is going to product. It is going from here, here, then coming down from there, right? Anyway, I'm only interested in state function in going from reactant to product, so I don't have to worry about this. Reactants are here, products are here. Right? This is on what scale? It is on enthalpy scale, right? Y-axis. Yes or no? Is
Yes,
this
sir.
not, is this not
Yes,
heat of
sir.
reaction at 1000 degrees centigrade?
So
Yeah, Arya.
I think we can derive it like that.
No, don't derive. Don't derive. Is it okay? Is it okay? You had asked a question that you had asked me to repeat this. How in going from point 1 to point 2 is heat of reaction at 1000 degrees centigrade?
Yeah, that I understood. Yeah.
That you understood, na? Okay.
Yeah.
Fine, fine. Now, same thing can I do at 25 degrees centigrade?
Yes.
All right. So same thing if I do at 25 degrees centigrade, I take my reactant, let's say point number 3. What are the reactants? Methane and carbon dioxide. I take them to products. Let's say point number 4. What are the products? 2 of carbon monoxide and 2 of hydrogen. This I already know. This is nothing but standard heat of reaction. What was the value? That standard heat of reaction was 247. Right. So instead of going from 1 to 2, can I not go from 1 to 3, 3 to 4, and 4 to 2? Do you agree with that?
Yes, sir.
So the change in going from 1 to 2, that is nothing but heat of reaction at 1000 degrees centigrade. Is it not the same as going from the enthalpy change? I will not write delta H, I will write it in words. Enthalpy change from 1 to 3 plus enthalpy change from 3 to 4 plus enthalpy change from 4 to 1. Do you agree with this?
Yes, sir.
Yes,
What
sir.
is the enthalpy change in going from 1 to 3? It is from 1000 degrees centigrade to 25 degrees centigrade. I have to take one CH4 and one CO2 from 1000 degrees centigrade to 25 degrees centigrade. What is enthalpy change from 3 to 4? Is it not just the heat of reaction at 25 degrees centigrade, standard state? Plus, what is the enthalpy change from 4 to 1? Is it not 25 to 1000 degrees centigrade? I have to take now 2 of carbon monoxide and 2 of hydrogen. Do you agree with this? So, is it not 1000 to 25 Cp of CH4 plus Cp of CO2 into dt plus heat of reaction plus taking something from 25 to 1000, 2 of carbon monoxide, which means 2 multiplied by Cp of carbon monoxide plus 2 multiplied by Cp of hydrogen dt. So would it not be simply delta H for the reaction and delta H for the reaction at 1000 degrees centigrade? That's our left hand side. Can I not switch the sign, flip this integral and put a minus sign? Would it not be 2 times Cp of CO plus 2 times Cp of hydrogen minus Cp of CH4 minus Cp of carbon dioxide into dt? This is your Kirchhoff's law. You had mugged up all kinds of things. If you want to take away one takeaway from this class, from this subject, it is this. Whole your life, right from 7th standard or maybe 5th now or 3rd or junior KG or whatever, nursery, you have been mugging up everything and you have been writing it in the exam and getting marks and thinking that you know something. Welcome to reality. All we have done is to look at, say that enthalpy is a state function. this statement also you must have mugged up. We had already done these things. We had already done these things for water. We had already done these things for water. Energy balances without reactions. Where did that go? We had already done these things for water. Do you remember? Latent heat of water, where did we calculate? We must have calculated somewhere. Didn't we derive this formula? Latent heat of water. Did we not derive this formula? Only thing is you have not thought of water change of phase as a reaction, isn't it? Can we go forward? Yes or no?
Yes, sir.
Yes, sir.
Okay. Now, how many of you have some kind of textbook with you? Either soft copy or hard copy. It doesn't matter. So I'm going to ask you to actually calculate the delta H for this reaction at 1000 degrees centigrade. I want you to actually take CP values for carbon dioxide, carbon monoxide, hydrogen, methane as a function of temperature, A plus BT plus CT square, and actually evaluate this integral. And remember that CP values, sometimes they are given in terms of kelvins. So we have to think about not 25, we have to think about it as 298 to 1273, 1000 degrees centigrade. Remember the CP values I gave you as a function of temperature. Do you remember this? I gave you CP values as a function of temperature. Yes or no? Do you remember or you don't remember?
Yes, sir.
So
Yes,
their
sir.
temperature had to be in Kelvin and CP was in terms of calories per gram mole of the substance per Kelvin. So take out your Himmelblaus book or any other textbook that you have. Oh, where? Yeah, this is the book. Right? So in the book, if you again go to these appendices, there are heat capacity equations. So in this particular case, appendix G. So here it says these two things: heat capacity for organic and inorganic compounds at low pressure. So low pressure in the sense 1 atmosphere. Don't worry why this star is there. You will come to know why that star is there later. But this is the CP equation. These are the CP equations. These are the CP equations. And it gives you A, B, and C values, and D in this case as well. Only thing is units are different. CP is in joules per gram mole, Kelvin. And temperature is in, I think, Kelvin. Okay. So look at your textbooks. Find out the CP values for different things. Methane is one component. Methane is there. Right? Carbon dioxide is one component. Carbon monoxide is one component. So both components are there. Hydrogen is one more component. So hydrogen is there. And find out actually the heat of reaction at 1000 degrees centigrade. Can you do that?
Yes, sir.
Try. So another point, so this is one life skill. Another life skill, knowing where to find information and knowing what information is required and where to find that information. This is all that you require. You should be able to derive anything you want, and you should be able to find parameters like CP in this particular case. Okay. So as we come to closer and closer of the semester, I'm going to give you less and less information, and I'm going to ask you to find more and more information for yourselves. So now find CPs or your own, for these compounds from your own textbook or wherever, Google, whatever you want to do, and find out heat of reaction at 1000 degrees centigrade. Tell me the answer. Let's take 5 minutes for solving. Any answers? Your calculators can do integration for you. Have you tried doing integration on a calculator? Hello. Anybody around?
Yes, sir.
Yes, sir, we have tried.
So, Ansh, Hardik, have you tried doing it on a calculator, integration on a calculator?
Yes, sir.
Yes, I've tried it on a calculator, but I prefer using Desmos or something like that.
Okay.
Yeah.
Fine.
So I directly use the calculator.
Yeah, good. In any case, we should be able to do manually also by using trapezoidal rule or something like that. Suppose we are stuck on an island where there is no calculator, we should still be able to get the answer. You can write it in a sand and get the answer on sand. Anybody stuck ever on an island? No? Without calculators? Nobody stuck ever on an island without a calculator?
Sir, I'm getting the
So
answer
you are
as
stuck somewhere on an island. Which island?
no, sir. Never left the country, sir.
Oh, okay. No, even our country has so many islands. Anyway, okay. For jokes apart, answer.
Sir, I'm getting answer as 1209, 142.
1209.
12,942.
12,942.
Yes, sir.
Okay, units?
Kilojoule per gram mole of methane.
Okay. 12,942 kilojoule per gram mole of methane. That is one answer. So heat of reaction increases from 247 kilojoules per gram mole to all the way 12,000 kilojoules per gram mole. Something wrong, Praveen. Check your units. CP would have been joules or calories per gram mole. We are talking about kilojoules. Check your answer, Praveen.
Yes, sir. I didn't check it. It was joules. I thought it was kilojoules. So
No, whatever
now
units
it
of
is.
CP are there.
So now it is 260.
260. That is one answer. Praveen, did you use calculator? Did you use any other software? What did you use?
Sir, calculator.
Okay. CP values, where did you get from? You want to tell us your CP values?
Sir, Himmelblas book.
Okay, you got it from Himmelblas. Okay. Just one word of caution. If you are using Himmelblas book, just one word of caution. Remember, the Himmelblas book is giving you two forms of equation, equation 1 or equation 2. Equation 1 has A, B, C and D. Equation 2 has A, B and C. The exponents are different. It is B into 10 raised to 2, C into 10 raised to 5. So if it is in form 1, temperature units are also given here. Temperature should be taken in either Kelvin or centigrade, depending on whatever are the values for that particular substance. So be careful about that as well. Okay. So if you're taking temperature in degrees centigrade, your integration limits from should be from 25 to 1000. If your temperature is in Kelvin, in the correlation 1 or correlation 2, your limits of integration should be 298 to 1273. Take care of units. The book gives you all the information. You have to just read it properly. So for example, for acetone, equation is of the form 1. Equation is of the form 1. But in that equation, temperature is taken in degrees centigrade. Whereas if you're talking about, let's say, let's go down. If you're talking about, let's say, carbon tetrachloride, CCl4, equation is in the form 1, but temperature is in the units of Kelvin. Right? So depending on what is given as units of temperature, take the integration limits appropriately, either 25 to 1000 or 298 to 1273. Okay, any other answer? Okay, can you do this as homework? We will talk about one more point and then we will close. Yes, no?
Yes, sir.
Right?
Yes, sir.
Let me give you one more reaction and then we will talk about the next concept. Suppose our reaction is like this. Where did that go? Yeah. So suppose our reaction is like this. Methane combusting plus oxygen methane combusting plus oxygen giving us carbon dioxide and H2O liquid. That is our standard. Suppose 25 degrees centigrade we are talking about. Standard state. So delta H, 0 of combustion of methane. Where did that go? Suppose it is 890.4 kilojoule per gram mole. Okay. Can you tell me how much heat would be released by combusting of 1 kilogram of methane? Can you tell me that? How much heat would be released by combustion of 1 kilogram of methane? Somebody tell me.
So 55,650.
Right, 55,650 units.
Yes, sir.
Punch units.
Kilojoules, sir.
Kilojoule per kg of methane.
kg of
Right. This number is the amount of heat released by combustion of 1 kilogram of the substance. This is called as calorific value. Calorific value. So calorific value of methane is 55,650 kilojoule per kg. If you want it in terms of kilocalories, divide by 4.18, it will be like 13,313 or 13,313 point something 4 kilocalories per kg. Now, when we actually burn something, have you ever gone into the kitchen anytime? Anybody?
Yes,
Anybody
sir.
has gone into kitchen except for eating something?
Yes, sir.
Yes, sir.
Very nice. So in your kitchen, what is there? You have an LPG burner. It takes air from surroundings and you get a flame, right? Isn't it?
Yes, sir.
Now, in this particular case, when your LPG, let's say LPG is like butane, it's a propane butane mixture, but let's say it is propane and butane mixture. When this LPG burns, do you get water in the vapor state, or do you get water in the liquid state in the flame? The flame is at what temperature?
Vapor state.
Vapor state, right? Flame is at high temperature, 1000 degrees centigrade, maybe something more. And then you put your vessel in that to cook Maggie, isn't it? So for the purpose of heating, you can mute yourself. Yeah, thanks. So for the purpose of heating something, you want to cook Maggie, the reaction that is actually occurring is methane plus oxygen giving us carbon dioxide gas plus H2O in the gas state, isn't it? How will I get the heat of reaction for this particular reaction? Is if I add to this reaction, oops, delta H is minus 890. If I add H2O liquid going to H2O gas, I should balance also this reaction properly. What is the heat of reaction for H2O liquid going to H2O gas? At 25 degrees centigrade. Somebody tell me, is it not the same as lambda at 25 degrees centigrade?
Yes, sir.
Yes or no? What
Yes,
is the
sir.
lambda at 25 degrees centigrade? 540 plus 0.55 into 100 minus 25.
586.25, sir.
Right. 586.25 kilocalories per kg, isn't it? Can I get it in terms of kilojoules per gram mole?
Yes, sir.
Convert 586.25 kilocalories per kg. How much would it be in terms of kilojoules per gram mole of water? It takes so long to convert units. Something that we did in lecture 1. kilocalories per kg to convert to kilojoule per gram mole. Does it take so long?
So 44.109.
Yes.
So
34
1
or
minute, sir.
44?
Sir, 44.1.
So 44, sir.
44.1 kilojoule per gram mole. So if I want this reaction, if I want the heat of this particular reaction, I need to multiply this by 2 times and add it. Then I will get this reaction. Do you agree? So delta H for this reaction would be minus 890.4 plus 2 times 44.1. How much is that?
$802.2.
802.2 kilojoules per gram mole of methane. How much is it in terms of kilocalories per kg? How much heat would be released by combusting methane? 1 kg of methane, but water in the vapor state. In the earlier case, it is the heat released by combustion of methane with water in the liquid state. That was 55,650 or 13,313.4 kilocalories. Now how much heat would be released by combusting 1 kg of methane, keeping water in the vapor state? 802.2 would be released per gram mole of methane, kilojoules.
$11,983.15.
Yeah, 11. How much? 119.
83.15. 11983.
Yeah, kilocalories per kg of methane. So you see, I'm going to get much less heat out of burning 1 kg of methane, because now water is remaining in the vapor state rather than water coming in the liquid state. Obviously, I should. Do you agree with this? Yes or no? So this is also called as calorific value of the fuel that we are burning. This is also called as calorific value, but one is called as a higher calorific value when water is in the liquid state, and one is called as lower calorific value when water is in the vapor state. And this is actually what we are going to get. This is actually what we are going to get when we burn 1 kg of methane to cook Maggi. Because on the flame we are keeping our vessel, water is not going to condense, water is going to be in the vapor state. The flame temperature is high, 1000 degrees centigrade, 1200 degrees centigrade, 800 degrees centigrade, of that order. Okay. Or sometimes it is called as gross calorific value. and this is called as a net calorific value. Okay. LCV or NCV and HCV, higher calorific value. So one of the ways in which we generate energy is by burning fuels. So we need to look at what are the calorific values of different fuels. Okay, we will use all these in our calculations as we go along. Shall we stop here for the day? Yes, no?
Yes, sir.
Okay. So I'm going to share one video related to the calorific value of fuels. Okay. That's going to talk about different things taking from this point onwards. So look at that video. Okay. Again, so one last point. How many people have solved that multiple effect evaporator problem? Should I share the solution or should I wait for some more days to share the solution?
So can
So
you
wait for some more.
Please, could you wait?
Okay.
Yes,
So Mayur, how long should I wait? Till Sunday you want?
Yes, sir, this weekend.
Sunday would be good.
Okay, great. So I will share the answers, the video of the answers on Monday. Okay, but the calorific value video I will share today itself so that you can study more. All right, so shall we stop for the day? Let me stop recording.